Hi everyone, this is Team Shumin Jiang and Edward Xie, and this is our final project. I'm Shumin Jiang from the Friday 2:30 class. And introduction.
And this is Xie, Edward He. Our team name is Creative License. And let's Jiang introduce what we done.
Okay, so first is the outline. We'll introduce what we have done and our future plan and what we have learned. So the first part, we have the trivial part, is autocomplete and get position. So these two parts was easy, so I just show the running results. Like for the autocomplete part, we got TRA and we have those 4 results. And for the final location, we input Trader Joe's and it gave us the latitude and longitude. And next, we got the calculate edit distance. So I ran 2 methods, one with memo and the other without memo. For the with memo one, the time complexity is n square. And for this one, I create a 2D vector as a memo and to store the result of di-1j, dij-1, and di-1j-1. And I got my dij as the 1 plus the minimum of those 3. And this is the with memo one, and I got them without memo one. For this one, I use a recursive function with the calculate edit distance without memo. So run it again and again. Like I test with the example, welcome to USC and beat UCLA. So the result was 10, and the with memo one only takes 327 microseconds to pass the test, but the calculate edit distance without memo never give me an answer. And next is the shortest path.
And this part we use two classic algorithm, Dijkstra and Bell and Ford, to calculate the shortest distance between 2 places. And for Dijkstra, we established a priority queue. It's a minimum heap to save the runtime. For Bellman, it takes more time because it needs to visit all the nodes. And we find some tips to improve the Bellman Ford with early terminated if all the nodes are the same. And next page, we just have some results compared to the Google search. Technically, it's just the same, but Google have different transportation methods to choose. So we find shortest path from CVS pharmacy to Trader Joe. It's a very not far, and Ross to Trader Joe. It's a medium far, and from Trader Joe to Whole Box and the Trader Joe to their dog. As the PV shows, they just looks like the same. And the next page. And next page is the runtime analysis. Dijkstra takes less time for run, 2 for 6 milliseconds, and it's showing the PPT. And the time complexity of the Dijkstra is O, E plus V log A. It is faster than the Bellman Ford, O, E multiple V. Because Bellman will visit all the possible nodes until it finds instead. For Dijkstra, we use high priority because it is faster to quick sort. So for Bellman, we use on the order map to store every neighbor's visited until we find the path. So it takes lots of time. And next page. It's a cycle detection. We use bool to return it is in or out as well, and we got a stop graph, and we don't even need to plot the cycle to do whether the cycle exists or not. So it is also a DFS processing. So we try all the nodes with a stop graph. If there is a cycle detected, the DFS will visit its neighbors. Not if they are not parent nodes between 2 nodes, so we can say there is a cycle. And because it is a DFS processing, so the time complexity is O V plus E. And next page. It's a cycle detection result. We've just find the larger square range that we can find the cycle exists. In the mini square range, the cycle exists. And next page is a topological sort, deliver Trojan column, which is where the dependency and names mob locations. And the others processing again. If there is a cycle in the topological sort, we just return the empty vectors. So there were some cycle cases to show in picture, and we do extreme cases like it's a circle, so there is empty vectors, and because it is BFS again, so the time complexity is O V plus E. And the next page.
Okay, so I'll introduce the TSP for you. TSP is a very interesting part. So first method is the brute force, and it's like DFS search and doing this for all nodes and try all things and get the minimum one. And the next we got brute force with backtracking. So this one is like faster, it's faster than the last one since it's used backtracking, and we like check the current distance with the shortest one, and if it's like larger than the already shortest one, so we'll abandon this path and all paths based on it. And the next is the 2OP1. It's a very good method, I think. Like we get an initial path and select for pairs of 2 nodes and check if it makes the path shorter. So like if it makes it shorter, we can choose a new path and do 2OP again and again until we find the shortest one. Like any swipe cannot make it shorter. So I'll compile the algorithm. And so this one is the number of places. Like we try 8 place, 9 place, 10 place, and 11 place. Unfortunately, the 10 place and the 11 place takes like more than 10 minutes to run, so I couldn't give the data. But for 8 places, and we can see here is the microseconds for those 3 methods, and here is the result in miles. And then for the 9 places. And we can see the backtracking one is faster than the brute force one, but the 2OPT one is the like fastest. But for the result, we can see brute force and the brute force with backtracking get the same result, but the 2OPT one get the like larger ones, makes it like the accuracy part. The 2OPT one is not good as the brute force one and backtracking one. And the next part is the find nearby. So we haven't done this yet, but we got a future plan for it. Like we want to use the min heap based priority queue to store all the results and give at most k results, but can be smaller than k. But like in the circle generated by the radius are as the inputs of it. So what we have learned from that is first we learned a lot of DFS methods. Since like at least 3 or 4 parts need to use the DFS and the heap and the queue. This like we can use heap and the queue to save our time for the method. It takes like although it takes more like complexity, but it has smaller like make it faster. And we also use a lot of DFS. And that's all. Thank you guys.
Here.
I want to stop.